Chapter 20 is the first of two chapters about the carboxylic acid derivatives, in which we are looking at things that have three bonds to an electronegative element, like carboxylic acids themselves. In each of these substrates, there is a leaving group potential, all indicated here in blue, and they are not all equally reactive. In Chem Activity 23A Model 1, we looked at the relative reactivities and discovered that there's a larger delta positive on the acid chloride than on the anhydride, than on the ester or carboxylic acid, than on the amide, and that carboxylic acid negative ions have very little electrophilic character. We can indicate this relative reactivity using greater than and less than signs. In particular, acid chlorides are more reactive than anhydrides, which are more reactive than esters, which are similar in reactivity to carboxylic acids, which are more reactive than amides, which are very much more reactive than carboxylate ions. And one of the things to remember is that many nucleophiles will also act as bases and pull off a hydrogen on carboxylic acids, making the anion. So there are a very limited number of nucleophiles that can react directly with carboxylic acids. We've previously seen two additional compounds that will react with nucleophiles at the carbonyl carbon, and that is the aldehydes and the ketones. And we learned previously that aldehydes react more rapidly than ketones for electronic and steric reasons. If you wanted to fit them into the carboxylic acid reactivity for how reactive their carbonyls are, aldehydes and ketones are less reactive than acid anhydrides, but more reactive than carboxylic acids or esters at the carbonyl carbon. In this chapter, we do look at strong base nucleophiles reacting with the acid derivatives, and in Chapter 21, we will look at some weaker base nucleophiles reacting with the carboxylic acid derivatives. And the major mode of reactivity is nucleophilic acyl substitution. In Chapter 20 and 21, we'll be looking at reactions of these substrates. In Chapter 20, we're focusing on stronger nucleophiles. In Chapter 21, on weaker nucleophiles. And all of these reactions have two important fundamental steps, in addition to any acid-base reactions that might happen. Acid chlorides, being the most reactive, will react with all available nucleophiles without the presence of any helping agent, such as an acid catalyst. And it reacts via nucleophilic acyl substitution, which is a two-step process in which the nucleophile adds to the acid derivative to make a tetrahedral intermediate, which will then eliminate the leaving group, blue group on the acid derivatives as they're listed here, to make the final product. Now in the chem activities, including 23B, you'll get a chance to practice a number of these conversions of stronger and weaker nucleophiles adding to carbonyl carbons. But there are a couple of reactions that are not directly addressed in the chem activity. One of them is the haloform reaction, shown here, in which a methyl ketone becomes a carboxylic acid. And you wonder, what's going on here? Where did everything go? Where did the extra carbon go? How did a ketone do a substitution and oxidation to get to the carboxylic acid state? The haloform reaction is used as a functional group test specifically for methyl ketones. And in the qual analysis, the unknown portion of the laboratory, you may get the chance to do this if you have a methyl ketone or believe you have a methyl ketone. Under the reaction conditions, the haloform, the CBr3H, or it can also work with iodine, the iodoform, will precipitate out. Now this reaction again looks rather curious, and it goes through actually a series of reactions that we've seen before. To start with, we've got base and bromine. And base and bromine are able to do alpha substitution reactions. The haloform reaction starts by creating an enolate ion, and that enolate ion reacts with the halogen, in this case bromine, to create an alpha bromo ketone, methyl ketone. But there are still two hydrogens at this alpha position that can be removed by hydroxide, and actually having a bromine here increases the acidity at this position slightly because the bromine is pulling electron density away. And so we can substitute a second time. But since there is still an alpha hydrogen here, as long as we have an excess of base and bromine, we can substitute a third time by the same mechanism to create a tribromomethyl ketone. This tribromomethyl ketone will now react with one additional equivalent of sodium hydroxide, but since it doesn't have any alpha hydrogens, it will do nucleophilic attack instead to create a tetrahedral intermediate like the one above, but this time the leaving group is the tribromomethyl group. This creates a carboxylic acid and a tribromomethyl anion. It is the last step of the reaction, the transfer of a proton from the tribromomethyl anion and the carboxylic acid, that drives this reaction to completion. The carboxylate ion will hang out until we add an acid in the second step. So again, this was an alpha substitution reaction 3 times, followed by a nucleophilic acyl substitution reaction of a relatively strong base nucleophile, followed by a proton transfer. The final section of this video will address the reduction of carboxylic acid derivatives, and in particular, the acid chloride and hydride ester and carboxylic acid tend to reduce down, losing their leaving group, to aldehydes, and aldehydes, as we know, readily reduce to primary alcohols. So it's very tough to stop at the aldehyde stage because aldehydes are more reactive than most of these groups. On the other hand, amides do a slightly different reaction. They will reduce down, but they will lose carbonyl, and they will only reduce down under the presence of our strongest reducing agent, lithium aluminum hydride. After protonation of this species, you end up with a primary amine. Now, the reduction mechanism for all of the other carboxylic acid derivatives is the same. This mechanism is actually exactly the same as the one above, with the exception that our nucleophile is a hydride ion obtained from the lithium aluminum or sodium boral hydride reagent. Often the reagent itself will form a coordinating bond with the oxygen intermediate to help stabilize it, but we still go through a tetrahedral intermediate in which we then reestablish our double bond, creating the aldehyde. Of course, with strong reducing agents that are strong enough to reduce most of these, such as lithium aluminum hydride, we would end up not stopping at the aldehyde stage, but would readily reduce further by nucleophilic addition, and after protonation obtain our primary alcohol. The most interesting parts of these mechanisms that make them somewhat different from previous reactions is that the OH group will deprotonate with the strong base lithium aluminum hydride, and then an OAL group will leave. Likewise, an OAL group will leave in the reduction of amides to primary amines. So what if we actually want to stop at the middle? What if we want to make an aldehyde by reduction of a carboxylic acid reagent? As you can see, acid chlorides are more reactive than aldehydes at the top of the page, and therefore there ought to be a reagent that would be just strong enough to reduce the acid chloride and not reduce the corresponding aldehyde. Turns out that is a very hindered version of the lithium aluminum hydride. Instead of lithium and aluminum with 4 hydrides, 3 of those hydrides have been replaced by the highly hindered O-tert butyl group, which also electronically deactivates the aluminum. This allows us to very cleanly create aldehydes without further reduction. Our second way to produce an aldehyde directly is to start with an ester. Now, it looks like an ester is less reactive than an aldehyde, but if we use a certain reagent that coordinates with the oxygen atom, diisopropyl aluminum hydride, if you do it at low temperatures, very carefully, you can indeed isolate the resulting aldehyde without further reduction.